So today we have the pleasure to have Zhen, who is a PhD student at Bordeaux with Nadia Smirnova. He made his work in a theoretical nuclear structure in the shell model, and he actually defended his PhD a month ago, and is currently looking for a postdoc position. So I will now let him talk about his work of PhD and show us the results of this PhD. So then, please.
Okay, thank you, Luis. Now I will share my screen. And can you see my screen?
Yes.
Okay. Okay, first I would like to thank the organizers for giving me this opportunity to present my work. Okay, the title of my presentation is Advances in Many-Body Perturbation Theory for Closed and Open Shell Nuclei. I will start with a short introduction, and then I will briefly introduce the nuclear shell model and the interacting shell model. Then I will go to the main part of this presentation, the Brillouin-Wigner and the Rayleigh-Schrödinger many-body perturbation theory. And then I will give a short summary and some perspectives. First, the introduction. And this figure shows the degrees of freedom and the corresponding energy scales from the building blocks of hadrons, quark-gluons to the collective motion of the heavy nuclei. And our nuclear physicists are interested in this nuclear structure and the reactions. Understanding this nuclear structure and the reactions from QCD is one of the main challenges in nuclear physics nowadays. However, since QCD is non-perturbative at low energy region, so we cannot directly study the nuclear structure and the reactions from QCD. We have first derived internucleon interactions from Carroll effective field theory, which is an effective, low energy effective theory of QCD. And then we used to derive the internucleon interactions to perform the nuclear many-body calculations to study the nuclear structure and the reactions. However, there's one problem in this process that is related to the hard repulsive core of nuclear-nuclear interaction at a short distance as shown in this figure. And this strong repulsive core will induce the strong coupling between low and high momentum in the matrix elements of the nuclear-nuclear interaction. And this strong coupling will eventually slow down the convergence in the calculation, in the many-body calculation, in terms of the size of the model space. So in order to speed up the convergence in the nuclear many-body calculation, we need to decouple this high and low and high momentum coupling. And nowadays we have many methods to do that. We have the similarity renormalization group method, below K, or LS transformation, and so on. So we perform these kind of transformations on the original internuclear interaction to soften the internuclear interaction or to decouple the low and high momentum. And then with the softened internuclear interactions, we can perform nuclear many-body calculations to study the nuclear structure and the reactions. Okay, the key point is to solve the A-body-Schrödinger equation here. And the A-body-Schrödinger equation is the relative kinetic energy and plus the two-body, three-body, and many-body internuclear interactions. The most direct way to solve this A-body-Schrödinger equation is just to diagonalize the Hamiltonian matrix in a sufficiently large model space. That is the nuclear shell model. However, this nuclear shell model method is limited to light nuclei and cannot go to heavier nuclei at the moment because the size of the model space grows rapidly with the increase of the size of the number of nucleons. So one strategy to surmount this problem is to project the full model space Schrödinger equation into a small model space called P space with an effective Hamiltonian to reproduce a subset of the eigenvalues Ek of the original Schrödinger equation. So the problem is how to construct this effective Hamiltonian. We have many methods now. For example, the nuclear shell model with a co-coupled cluster, IMSRG. These three methods are non-perturbative methods, and they have achieved many successes nowadays. We have another method called many-body perturbation theory, which is the oldest method starting from 1915s. However, this many-body perturbation theory still has some open questions. For example, the order-by-order convergence of many-body perturbation theory in powers of internuclear interactions. This figure shows the ground state energy of oxygen 16 calculated from an iterative method of the Rayleigh-Schrödinger formalism of many-body perturbation theory. This is taken from this paper published in 2016. They have found that this kind of calculation eventually diverges in the harmonic oscillator basis, and it only converges in the Hartree-Fock basis. However, a harder potential can still spoil the convergence in the Hartree-Fock basis. So these are just some conclusions from numerical calculations. However, this kind of iterative calculation is limited to the light nuclei, and we cannot perform such kind of calculations for heavier nuclei. So a comprehensive understanding regarding the order-by-order convergence is still missing. So in the first part of this presentation, I will show the order-by-order convergence problem with the Brillouin-Wigner formalism of many-body perturbation theory. But the second open question is related to the diagrammatic calculation beyond third order. The diagrammatic calculation can go to heavier nuclei. However, all the previous calculations usually stop at third order because of the prohibitive number of diagrams beyond third order. One natural idea to go to high orders is to automatically generate and evaluate these diagrams. The first article that I can find to automatically generate diagrams was published in 1973. Recently, Atyu and his collaborators have developed a Python code called automatic diagram generator that can be used to automatically generate the diagrams and expressions used in many-body perturbation theory, the group of many-body perturbation theory coupled cluster, IMSRG. There was another paper published in 2019. They have included the diagrams up to the fourth order in the nuclear method calculation by automatically generating the code. Also, many works have been done recently regarding this automatic diagram generation. And there are still some interesting works that have not been addressed before. For example, the automatic diagram evaluation, numerically, for the ground state of closed shell nuclei beyond third order, and the automatic diagram evaluation, both analytically and numerically, for the construction of the effective Hamiltonian of the interacting shell model beyond third order. So in the second part of this presentation, I will show the automatic diagram generation and evaluation. And before going into this open questions in detail, let us first take a look at the nuclear shell model and the interacting shell model. As discussed before, the idea behind nuclear shell model is simple, just to diagonalize the Hamiltonian matrix in a sufficiently large model space. This model space is spanned by many-body basis. The commonly used basis is the M-scheme A-body harmonic oscillator basis. And these bases are the eigenvalues of the eigenstates of the A-body harmonic oscillator. And it carries good quantum numbers, the decomponent of the total angular momentum, the decomponent of the total isospin, the parity. However, since the harmonic oscillator has infinite number of eigenstates, we need to truncate such spaces. And we can use the Emax truncation, that is to limit the harmonic oscillator shell excitations to be smaller or equal to Emax. Here is an example with 4 harmonic oscillator shell excitation for the lithium-6. Another problem related to this M scheme about the harmonic oscillator basis is the superior center mass problem. We have included the superior center mass motion in this basis. Since we only have a minus 1 times 3 degrees of freedom. Here we use the Lawson method to remove the superior center mass motion from the low energy region. That is to add this extra term to shift the superior center mass motions into high energy region. Okay, the Nuclei shell model will be used to benchmark the calculations from many-body perturbation theory. We have developed a small Nuclei shell model code called Nuclei Configuration Interaction Lab that can be used to provide benchmarks for many-body perturbation theory. And here is an example for the Nuclei shell model calculation of the ground state energy of helium-4 with a Dijon-16 potential. Dijon-16 is based on SRT involved N3LO potential and fitted to the perpetuities of light nuclei by phase equivalent transformations. It is a soft potential. So we can see that as the increase of the model space from MX2 to MX10, the results, the Nuclei shell model calculation, converges to a value that is very close to the experimental value. And as discussed before, for heavier nuclei, we can project the full model space Schrödinger equation into a small p-space. And the common choice for the p-space is the 0 h bar omega model space. 0 h bar omega model space is a model space without any harmonic oscillator shell excitations. So for closed shell nuclei, this p-space is one dimension. And P and Q are the projection operators to the P space and the Q space, respectively. So for the closed shell nuclei, we can only calculate one eigenvalue, and that is the expectation value of the effective Hamiltonian in the P space basis state phi 0. For open shell nuclei, we have multi-dimensional P space. All the P space basis states have an inert core. In the interacting shell model calculation, we usually remove the ground state energy of the core and only consider the valence nucleons moving in the valence space. So the A-body Schrödinger equation is reduced to an A-body Schrödinger equation. A is the number of valence nucleons outside the core, and the effective Hamiltonian can be written in Fock space as in this form. This is the one-body part and the two-body part. Epsilon alpha are the theoretical single particle energies, and this is the two-body matrix elements of the effective interaction. Now we are ready to go to the many-body perturbation theory. First, let us look at the Brillouin-Wigner many-body perturbation theory. First, let us look at the exact solutions of the p-space Schrödinger equation. In practice, we split the Hamiltonian into H0, which is the unperturbed Hamiltonian, and H1. We use the eigenstates of H0 phi alpha as our basis of the model space, and so we can use the M scheme harmonic oscillator basis, which is the same as the Nuclei shell model. So the p-space Schrödinger equation can be written in this way with an energy-dependent effective Hamiltonian. And since this is an energy-dependent effective Hamiltonian, we need to solve this p-space Schrödinger equation self-consistently. In practice, we can solve the eigenvalues of the effective Hamiltonian. We solve this eigenvalue problem of the effective Hamiltonian at various energies E to have the eigenvalue function f and e at various energies E. And then we can find the intersections between y equal f and e and y equal e. These intersections are just the solutions of this p-space Schrödinger equation. And here is an example for the ground state energy of helium-4 from Dijon 16 at its power omega 18 MeV and max 2. Since it is a small model space and max 2, so we directly construct the effective Hamiltonian by taking the inverse of this E minus QHQ operator. So this kind of construction for the effective Hamiltonian is an exact way to construct. Since the helium-4 is a closed-shell nucleus, so we have one-dimensional p-space. So at one energy E, we only have one eigenvalue for the effective E. And the eigenvalue of the effective Hamiltonian is depicted with this dashed line. The intersections of this dashed line with the line of y equal e, which are labeled with this red dots, are the solutions of the p-space Schrödinger equation. And these red dots can be reproduced by Nuclei model calculation exactly. There are some properties for this eigenvalue function. The first one is that we observe some singularities of this eigenvalue function f and e. These are just the eigenvalues of the QHQ operator. And another feature, we can see that the slope of the eigenvalue function is negative. And at each intersection, the first derivative of the eigenvalue function is proportional to the ratio of the Q-space occupation probability over the P-space occupation probability in the full model space wave function. This full model space wave function can be written in the P-space part plus the Q-space part. This is the example for helium-4. We can also go to open shell nuclei. This is the example for lithium-6 for G pi equals 0 plus, 1 plus, 2 plus, and 3 plus. Now we have multi-dimensional p-space. For example, for G pi equal to 0 plus, we have a two-dimensional p-space. So at one energy E, we have two eigenvalue functions. And other properties are similar to the previous case of helium-4. The intersections are the solutions of the p-space Schrödinger equation. All these calculations are performed at a small model space and max 2 model space. And if we want to go to larger model space, we cannot directly reverse this matrix E minus QHQ, since it is impossible for large matrix. So that is why we need a perturbative expansion to calculate or to construct this effective Hamiltonian. In practice, we can expand this 1 over E minus QHQ into a geometric series, which is written in this way with the ratio R. And in this process, we have split the denominator into an unperturbed part X and a radial interaction part Y. X is diagonal in the Q space, so that we can easily calculate its inverse 1 over X. And here we have introduced a partitioning parameter Gaussian in order to tune the convergence behavior of this perturbation series. So the main problem of this kind of calculation is that whether this kind of calculation is converging or not. And luckily, this is just a geometric series, so the convergence criterion is just rho r smaller than 1. Rho r is the spectral radius of R. The spectral radius is just the maximum absolute values of the eigenvalues of R. And we can prove that for energy E smaller than the lowest eigenvalue of the QHQ operator, which is denoted with E1 QHQ here, we can always make this perturbation series converging by taking a large enough Casset. From this, we can develop two very important conclusions. The first one is the ground state calculation can always get converged due to the variational principle. And this can be generalized to each lowest G pi state because the quantum number J and Chi are good quantum numbers. And these are the universal conclusions and are independent of the choice of basis and the choice of the internucleon interaction. So we expect that no matter it is soft or hard nucleon-nucleon interaction, we can always get converged result for the ground state and each lowest G pi state. Okay, let us then check these conclusions numerically. In order to do that, we need to go to high orders of this effective Hamiltonian. In practice, we can directly multiply this R matrix many times to go to the high orders of this effective Hamiltonian, but this is not efficient. Instead, we have introduced the K-box method. The K-box is defined in this way. This can be seen as the renormalized H-band vertex in the PQ space. With this K-box, we can easily construct the effective Hamiltonian with the second order, with first order and second order. And this K-box actually can be obtained by performing this iterative equation from K0 equal to 0. After each iteration, the K-box, the effective Hamiltonian, the K-box after each iteration is corresponding to a specific order of this effective Hamiltonian. And also the full model space wave function can also be obtained from this K-box. And this is a very efficient method compared to the first method. And now let us go back to this ground state energy of helium-4. As we discussed before, this dashed dotted line is the eigenvalue function of the effective Hamiltonian calculated by the matrix inversion method, which is the exact way to construct the effective Hamiltonian. So this dashed dotted line provides benchmark for the perturbative calculation, and the nuclear model result for the ground state energy of helium-4 is labeled with this red dot. We see that indeed at the intersection of this eigenvalue function of y equal a, we have this ground state energy of helium-4. And here we choose Casset equal to the expectation value of H1 in the phi 0 state. Phi 0 is the p-space basis stage. It is one-dimensional, so we only have one p-space basis state, phi 0. And with this Casset, we have also calculated the value of rho r. We see that in the energy interval from -32 to 54 MeV, rho r is bigger than 1, which means that the Brillouin-Wigner perturbation series is diverging. And the ground state energy, this red dot, is inside this divergent interval. So our Brillouin-Wigner perturbative calculation will eventually diverge. Now let us see. This is the second order calculation, and third order, fourth order, fifth order, 15th order, 13th order, 45, 16, and 1000. So it eventually diverges with this kind of Casset. And we can also perform Padet approximation to obtain a converged Padet series. We see that from Padet 1,1 to Padet 2,2, Padet 3,3, we can get the converged Padet series. that is very close to the exact value. And recall that we have concluded that for the ground state energy calculation, we can always make it converging by choosing a large enough Cathay. So now we increase Cathay from minus 132 MeV to minus 110 MeV. And now the divergent interval which is 1.0 to 66.9 MeV is shifted to the right of the exact ground state energy, and that at this exact ground state energy, the value of rho r is about 0.5 MeV. So the perturbation series is converging with it. Indeed, our perturbative calculation is converging to the exact result. And this 1.081 is nothing but the lowest eigenvalue of the QHQ operator, and is also the lowest singularity of the exact F and A. If we increase the parameter Cathay further to 0 MeV, again, we can still get converged result. And however, the rho r is a bit larger than the previous one, so the speed of the convergence is slower than the case of minus 110. Even with the bare and 3LO potential, bare, I mean unsoftened, it is a hard potential, we can still get converged results with the Cathay parameter to be 0 MeV. Now we can let us go to the open shell nuclei. This is the helium-6 at different J pi equal to 0 plus, 1 plus, and 2 plus. It is similar to the previous case with the choice of Cathay to be the expectation value of H1. We found converging series. And the previous calculations are performed at max 2, and we can also go to larger max. Here are the calculations for the ground state energies of helium-4 and oxygen-16 at max 8 and max 4 with the Dijon-16 potential, which is the soft potential. And we see that the converged perturbative calculation can reproduce the results of nuclear shell model exactly. And now let us see what happens with the hard potential and the bare and 3LO potential. Well, still we can get the converged result, and the converged result can be reproduced by the nuclear shell model exactly, both in the harmonic oscillator basis and in the Hartree-Fock basis. And for open shell nuclei lithium-6, we have similar result. Here is the 0 plus to 0 plus and to 1 plus stage. We can see that at high orders, the energy is converging, and the difference between the many-body perturbation theory and the nuclear shell model become smaller and smaller as we increase the order. And even with the bare and 3LO potential here, we still get converged results. So let us summarize the previous results. We have performed some numerical calculations, and we get converged result in both harmonic and Hartree-Fock basis, and we get converged result with both soft and hard internuclear interactions. And this may challenge the traditional idea of the non-perturbativeness of the bare or renormalized unsoftened hard internuclear interaction. And since we are working in the Brillouin-Wigner formalism for this order by order convergence, in principle, once we have the converging Brillouin-Wigner perturbation series, we should be able to obtain a converging Rayleigh-Schrödinger series by expanding the effective Hamiltonian around a fixed energy near the exact eigenvalue. And now let us go to the Rayleigh-Schrödinger many-body perturbation theory. The previous iterative calculation cannot go to heavier nuclei. The diagrammatic form of the Rayleigh-Schrödinger many-body perturbation theory is suitable for heavier nuclei calculation. And in this Rayleigh-Schrödinger formalism, we use the energy-independent effective Hamiltonian. By expanding the energy-dependent effective Hamiltonian around a fixed energy omega 0, so that we can have the energy-independent effective Hamiltonian. It can be constructed iteratively by iterating this wave operator omega. It is much more complicated than the Brillouin-Wigner formalism of the effective Hamiltonian. And for the Grothin energy of closed shell nuclei, since the p-space is one-dimensional, and we denote the p-space state with this say, so we can only calculate the Grothin energy of the effective Hamiltonian, which is just the expectation value of the effective Hamiltonian. And here are the different orders of energy corrections to the Grothin energy. And we can simplify these formulas using the Wick theorem. And we can also draw the corresponding Feynman diagrams and summarize the diagram rules to use diagrams to perform these such kind of calculations in order to get rid of the tedious Wick calculations with Wick theorem. It turns out that all the non-zero contributions for the to the Grothin energy of closed shell nuclei are linked diagrams. So this is the link diagram theorem. And for open shell nuclei, it is a bit more complicated. We perform a similarity transformation on the original Schrödinger equation to have a p-space Schrödinger equation with an effective Hamiltonian depending on an operator chi. This operator can be obtained by solving this decoupling equation. Instead of this effective Hamiltonian, we can also define an effective interaction, which is just H effective minus H0. We have many methods to solve this decoupling equation, which are shown here. All these methods need the information of QE and QME, which are the Q box and the derivatives of the Q box respectively. And the definition is shown here. It turns out that the diagrams contributing to the Q box are just the valence-linked irreducible diagrams. And for one-valence nucleon system, we have one-body Q box diagrams, which can be used to derive the theoretical single-particle energies. For the two-valence nucleon system, we have two-body Q box diagrams, which can be used to derive the two-body matrix elements of the effective interaction used in the interacting shell model calculation. In all these diagrams, the core diagram have been removed, so the Grothin energy of the core have been removed. And we have developed a program that can be used to automatically generate and evaluate these diagrams used in the Grothin energy calculation and used in the construction of the effective Hamiltonian for the interacting shell model. So we have generated the diagrams used in the Grothin energy from the first order to the sixth order, and also from the first order to the fifth order for the Q box diagrams. We have also benchmarked the generated diagrams by performing the iterative calculations. And we see that the iterative calculation and the diagrammatic calculation are exactly the same. So now we are safe to perform actual calculations with these generated diagrams. And here is the example for the Grothin energy of helium-4 in the harmonic oscillator basis with the Dijon 16 potential up to from first order to the sixth order, and in the model space from max 2 to max 10. at the increase of max, we see that the h bar omega dependence becomes weaker and weaker, especially for high order results. However, we cannot conclude that the perturbation series is converging or not. Instead, we see some oscillations near the exact nuclear model result. However, we can perform Padilla approximation to get the converged Padilla series. For example, at the max 10, we have Padilla 1, 1, 2, 1, 3, 1. We see that the converged Padilla series is very close to the nuclear model result, and Padilla 3, 1 needs the calculation up to the fourth order. And this is a calculation in the Hartree-Fock basis. So unlike the case in the harmonic oscillator basis, this kind of calculation converges quickly. We see that from the Emax2 to Emax6, from the first order to the fifth order, the result quickly converges to the to a value that is very close to the experimental value. And here are the calculations for the ground state energy of option 16 in the harmonic oscillator basis. Here we see that from the first order to the fifth order, again, we cannot conclude it is diverging. Instead, we may conclude that it is diverging. Again, we perform Padilla approximation. Well, it is much better than the original perturbation series. From Padilla 1, 1 to Padilla 3, 1, the result is very close to the experimental value. And this is the calculation also for the ground state energy of option 16 in the Hartree-Fock basis. Again, in the Hartree-Fock basis, the order by order convergence is it's much better than in the harmonic oscillator basis. And finally, I would like to show the low-lying positive parity states of lithium-6 calculated from the Cubox diagrams up to the fifth order using the Dijon 16 potential in the harmonic oscillator basis. And these are the calculations at the second order, third order, fourth order, fifth order, and this is the experimental value. This is the calculation, the interacting show model calculation with the phenomenological effective Hamiltonian Cohen cross 1, CK1. The results from many-body perturbation theory are labeled with these horizontal lines, whereas the results from nuclear model are labeled with the stars. We can see that with the increase of order, the correspondence between the nuclear model and the many-body perturbation theory becomes better and better. For this low-lying states, however, for these higher states, the correspondence is still not very good. Now, this may be explained as follows. In the nuclear model calculation, for example, at the max 8, we have 8 particle, 8 hole, actually not 8 particle, 8 hole. We have at most 6 particle, 6 hole excitations. However, in the many-body calculation, many-body perturbation theory, we do not have such high particle hole excitations. So that may be explain why the correspondence for the high stage are not very good between many-body perturbation theory and the nuclear model. Since these higher stage for these high states, the high particle hole excitations might be important. So finally, I will give a short summary, and we have developed a new nuclear model code called the Nuclear Configuration Interaction Lab, and we have in the Brillouin-Wigner many-body perturbation theory, we have introduced a general partitioning parameter And we have proposed convergence criteria. And more importantly, we have concluded that for each lowest G pi state, the Brillouin-Wigner perturbative calculation can always get converged due to the variational principle and the conserved G pi quantum number. And we have also introduced an efficient K-box iterative method to calculate high orders of the effective Hamiltonian. And in the second part of this presentation, we have shown that we developed a program that can be used to automatically generate and evaluate both analytically and numerically the diagrams used in many-body perturbation theory, and some numerical calculations have also been done with these generated diagrams. And here are some perspectives. We can optimize the code of the K-box iterations to go to heavier nuclei, and we can introduce 3 nuclear forces. And also we can construct other valence-space effective operators with the K-box and the generated diagrams. We can also introduce new partitioning scheme to the Rayleigh-Schrödinger many-body perturbation theory, especially in the diagrammatic form to tune the convergence behavior. And we can also optimize the automatic diagram evaluation code to go to heavier nuclei and to construct higher shell effective Hamiltonians. We can also generate 3-body Q-box diagram and construct 3-body valence space effective Hamiltonians. And we can also develop a new non-perturbative diagrammatic method from the K-box iterative equation, and so on. Okay, thank you for your attention.